Hi guys, let's do shortest path in binary matrix. So we're given an n by n binary matrix called grid, and they want us to return the length of the shortest clear path in the matrix. If there's no clear path, then they want us to return -1. So a clear path in a binary matrix is a path from the top left cell, which is 0, 0, to the bottom right cell, which is going to be n minus 1, comma n minus 1, where n is the length of the grid, such that all the visited cells of the path are 0, and all of the adjacent cells of the path are 8 directionally connected, which means that they are different and they share an edge or a corner. So the length of a clear path is the number of visited cells of this path. So in example 1, they give us this grid and we would output 2 because from the top left corner, which is coordinates 0, 0, right, row 0, cells, or column 0, to get to the bottom right corner, which is n minus 1, comma n minus 1, then we would visit 2 cells. We would visit the top left one and the bottom right one because we would go diagonally this way. So that's why we return 2. So in example 2, they give us this grid and we would output 4 because starting from the top left corner, to get to the bottom right corner, we can take this. This is the shortest path possible. So we would from here go right, which is 2, or starting from here, technically that's 1 node. Then to get to here, that's 2 nodes. To get to here, that's 3 nodes. To get to here, that we visited 4 nodes. So we'd output 4. And then in example 3, so if I actually make this grid in a better format so that we can see what's going on, then we can see that starting from the top left corner, this actually has a value of 1. So we can't go anywhere because this is a 1. So we would just return -1 because there's no possible path to get from here to here where we only visit cells that have a 0 in it, right? Because this one right off the bat already is a 1. So it's not possible. Okay. So in this case, so because we want to find the shortest path, we know that we need to do a BFS. Anytime we want shortest path in a tree or a graph, I believe, then we're going to want to do a BFS instead of a DFS because we're exploring essentially like layer by layer. So we're always going to find the fastest route to the destination with BFS. DFS could if we did DFS, for example, it could actually give us the wrong output in this case because let's say we're starting in the top left node, right, 0, 0, and then we explore right as far as we can until we hit the wall because DFS goes as deep as possible one way before it goes another way, right? So we go as far right as possible, that's 1, 2, 3 nodes, and then we hit a wall, so then we go down. Well, then we go 4, 5, right? Because this was 1, 2, 3, 4, 5. And then we do reach the destination, but we essentially counted an extra node. So that was not the fastest possible path if we do DFS. So we pretty much need to use BFS in this case. Okay. And then, so let's just take care of our base cases first. So if our starting cell or our ending cell is not a 0, right, because this is a 1, then we're going to just return -1 because we already know that there's no possible path if that's the case. So if grid at 0, 0, not equal to 0, or grid at grid.length -1, grid at 0.length -1, not equal to 0, return -1, right? So that's our base case. And then we also need to set up a array, like a 2D array to represent our possible directions that we can take because this is going to help us in visiting our neighbors of a cell because we need to be able to go right, down, diagonally, right and down, and so on, right? In all the possible 8 directions. So this is just going to make it a little bit more clear, what direction we're taking, if that makes sense. So we're going to set up a 2D array of directions. And in here we're going to say -1, -1, -1, 0, oops, -1, 1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, 0, -1, 0, 1, 1, -1, 1, 0, and 1, 1. Semicolon. Okay, so basically what's going on here is like this is just like to keep track of the possible directions we can take. So negative in this case, well the first element in the each like inner array, I guess, is representing the row, and the second one is representing the column. So -1 for a row means we're going up in rows, right? Because like if we start at like 1, 1, then if we go up a row, or okay, this is -1, -1. So let's say we go up a row, which is -1 in the row 1, then we're moving up to here, right? If we started here, we're moving up to here because this is from 1 to 0 for the row. In this one, if we move -1 in the column, then if we're at column 1, like let's say we're here now, then if we move one column minus, that takes us from 1 to 0, so then we're moving to the left. So minus for row means up, positive row means going down. So like plus, this one would mean like we're going down. -1 for the column means we're moving left. +1 for the column means we're moving right. Okay, and then 0 means we're just like not moving either way for that direction. So that's going to help us out later on for visiting a cell's neighbors. And then we're going to want to set up our queue to start our BFS. So our queue is going to store an int array because we're going to store the cell that we're currently at. So it's going to be an int array. Queue is new linked list. And we're going to want to add the top left cell into the queue because that's our starting point, or like our root for this in this problem, right? So queue.add, we're gonna make a new array, and we're gonna put 0, 0 because that's the starting cell. And then I'm also actually just gonna store the number of nodes that we've visited in here as well to keep track of. So this is gonna be row, column, and steps, or like number of nodes visited, right? And we're going to increment this every time we visit a new node. That way, like when we get to the bottom right, we can just like easily access this number and return that. And it'll just be like a little bit easier. Okay, then we also, so to keep track of visited nodes, in this case, you can do it two different ways. You can either make a 2D Boolean array of the same size of grid, so like this exact same size, and then it just stores true or false instead of numbers to keep track of if you've seen that node or not. Or you can do what I'm going to do, which is just overwrite the value if we've already visited it. Because if we change this value to 1 after we visit it like that, then like for this one, we know that we are like, this is a 1, so we're not going to go back this way because we're not going to visit any nodes that have a 1 in it. So that's like another way. So I'm just going to mark that as a 1 so that we don't go back to it. So grid at 0, 0 equals 1. Okay, so then this will change to like that basically, and then we're not going to go back to it. Okay, so our queue will start off as empty, or actually no, it's not empty. We put this in here. Okay, so we currently have this in our queue, and this is now a 1. Okay, so now we are set to start our BFS. So we're gonna start our while loop. So while our queue is not empty, then we'll continue doing our BFS. So we want to remove the top node or cell off of the queue. So we're gonna say int cell is queue.remove. Now we have an empty queue because we just removed it, but now we have this stored in this variable cell. And then I'm just going to assign variables to each of the values in here so that we don't have to keep accessing like cell at 0, cell at 1, cell at 2, you know. So int row is cell at 0, column is cell at 1, steps is cell at 2. Okay. Then if we're at the bottom right corner, so like let's say we have a singular cell as our grid, right? We only have this one cell which has a 0 in it, then let's say, then that means like we are already at our destination, right? This would technically be the bottom right of the cell. Well, if that's the case, then we can just return the number of steps that we have, which is going to be steps, right? So if that's the case, so, okay, I'm gonna make an if statement to check that. So if our row is grid.length minus 1, and our column is grid at 0.length minus 1, that means we reached the bottom right corner, and we can just return steps. Okay, and then if not, so if this is not the case, that means we're not at the bottom right corner yet, and we're gonna need to do a little bit more work to find the shortest path to get there. So if that's the case, then we're gonna explore each of these directions, like, or whichever one is possible, depending on where we're at. So actually we're gonna do a loop for all the directions. So for int direction in directions, we're going to make our new row the current row plus direction at 0. So we're basically looping through each of these one by one. Okay, and for every single direction, remember the first element is going to be the row, like the direction that we're moving for the row, and then the second one is the direction that we're moving in for the column. So our new row is going to be our current row plus this, which is minus 1. So if we're currently at 0, then this would technically be like row -1, which wouldn't work. Like, we're not actually going to explore that because it's out of bounds, which we're also going to check for. But just like, so you understand what's going on. Like, let's say we're actually at like this one or something, then our row would turn into 0, right? Because it's our current one, which is 1, plus -1, which means just minus 1. So 1 minus 1 is 0. So we would move up to row 0, basically, in this case. But we're doing that for every single direction. That was just like one example. We're also doing that for every column. So we can say int new column is column plus direction at 1, because the in element 1 is the direction for the column. Okay, and then we're going to want to check if this new row and new column is in bounds, because if it's in bounds, we want to explore it, and if it's not in bounds, then we'll just skip over this whole statement. So if new row is greater than or equal to 0, and it is less than grid.length, yeah, and same for the column. Okay, and then we also need to check that the value of this new cell, like basically like right, because it's a new row, new column, which is a new cell, actually has a value of 0. Because if it's a 1, then we also can't explore it anyway. So we need to make sure it's a 0. So and the grid at new row at new column equals 0, then we can actually explore it. So if we explore it, then we'll set that value equal to 1 to represent that we visited it. And we will add it to the queue to explore in the next like layer of our BFS. So queue.add, we're going to make new column, or sorry, new row, new column, and then we're going to increment steps by 1, because now we're adding a new cell into the queue to be explored, and so that's a new step. And if we did this for the entire grid, and we're not able to get to the bottom right corner, because we only actually return the number of steps here if we were able to reach the bottom right corner. But like, let's say this is a 0 and this is a 0, and then everything else in the grid was 1s, then we can never actually reach here. So if that's the case, we explored every possible direction and we couldn't get to the bottom right, then there's no possible path, so we would return -1. So let's check that. All right, so this is going to have a time complexity of, let's see, O of n squared, okay, where n is, I don't know what you would really call this, like the length of the grid, or like I guess technically the number of cells. No, because then I don't know, but you guys get what I'm saying, right? Like the n by n grid. So n is like one side of this grid. I'm just gonna say length of grid, okay? Because it's going both ways, which is why we get the n squared. Otherwise, like if this was not n by n, like if it was n by m or something, where these are like different lengths, then we would say n by m. But yeah, basically I'm just saying that the time complexity is the same size, like relative to the grid, okay? I hope that makes sense, but let me know. But basically the reason for this is because, so if we think about the worst case scenario for this problem, that would be that the entire grid was only filled with zeros, because since BFS, like it starts from here and then, or like let's use this one because it's bigger, it starts from here and then we explore like every layer, right, at one time, then if every single one is a zero, we're going to explore every single node in the grid, because we need to get to the bottom right. So if that's the case, we're exploring n squared. We're visiting every single cell in this grid, right? And that's n squared. And if we think about the code as well, so this doesn't matter because that's constant. Let's go down to the loop here. So the while loop, right? While the queue is not empty, well, okay, this is looping through each direction here, which I guess is technically constant because we have a constant number of directions, which is 8. And our queue, all right, let me think this through. So our queue in every layer is going to store every node in this layer, and then we remove it. But in the end, yeah, I guess we would store each like layer at a time. But I guess that's like still proportional to the size of the grid. So I guess that also actually makes the space complexity the same thing, even though like technically it's like smaller, but like it's still scaled relative to the dimensions of the grid. So if that makes sense. Anyways, yeah, but like as we add to the queue, then the time complexity is like running along with it, which is going to be n squared. I don't know if that explanation made any sense, but let me know. I can still try to answer any questions if you guys are still confused, but yeah, that's it for this problem. Thank you guys for watching, and like and subscribe if you found it helpful. Bye!